Hey friends, this is a video from old Ben. This is for Calc 3. This will be the last video from the Calc 3 class for fall 2021. I promised y'all that I would make a video about the remaining examples from change of variables. The fact that you did not have them prior to now should not affect your studying for the exam, but here are some more examples to work out and stuff. So anyway, I do want to apologize about that. Just to let you know, I'm clearly missing a little bit of time going on about yesterday because I did not have sleep the previous night. I'm making excuses, but in any case, here we go. All right. So I'm going to share screen as per usual and jump over here to the iPad. And as you'll see, we are looking at exercise 3, which was an example that we did not do. All right. So what we're going to have to do is to take a couple of things with it. First of all, I'm going to go ahead and figure out the Jacobian because we've got stuff set up where that is a pretty straightforward process, right? Now, if it gave you u equals functions of x and y, and they were nice functions of x and y, you ought to be able to solve for them, okay? But in this case, we have been given x and y in terms of u and v. And when we say take the partial of xy with respect to uv, then if we didn't say to take the determinant, we would have to go through here and across the top. Remember, we're doing the partial x with respect to u, partial of x with respect to v, and then y across the bottom. Okay, so with the stuff that we already have in place there, and I'm expecting y'all to look at these equations. I'm not copying them down. X with respect to u is going to be 1 minus v, and x with respect to v is going to be minus u. Then for your y's, you're going to get v and then u. Okay, so the thing that we actually need here is going to be the Jacobian. I'm sorry, that the determinant of the Jacobian matrix. You will note that which thing to call the Jacobian sometimes is a little bit unclear, but the 1 minus u, try it again then, 1 minus v times the u, that's the main diagonal, minus v times the minus u. So if you multiply those out, you get 1 minus uv plus uv, which is 1. Yay! I say yay because we turned out to get something that's very simple to work with. So when we do our integral there, we're going to insert something, but the something we insert is just a 1. No sweat, right? Okay, so real quick here, I want to do a sketch of what this region looks like in the XY plane. And then we're going to look at what it looks like in the UV plane. So in the XY plane, it said X and Y are both greater than or equal to 0. So that tells me that I need to be thinking about things in the first quadrant, okay? I'm not marking anything down for that yet, but just remember we're here in the first quadrant. And then the next bit of it says that X plus Y is between A and B, okay? So if we want to figure out what that looks like, you have to think about the line X plus Y equals A, and then of course equals B. And the assumption from the way it's written is that A and B are going to be numbers so that A is less than B. And so we should get two parallel lines like so. And maybe I'll move this one in a little closer so that it's, clear that they're farther apart. And so one of them will be x plus y equals A, and the other will be x plus y. Come on. X plus y equals B. And so for any value in between there, we get that, okay? So now we want to think about that with the UV plane. And you can just substitute in the things that you need and see what happens here, okay? So we need to talk about I guess I didn't label it here. X equals 0, y equals 0, for these boundary pieces there, all right? So for x equals 0, that's going to convert to saying u minus uv equals 0, which means that you have to think about either the line u equals 0 or the line v equals 1. So that'll be a little bit of a hassle, but just because of the fact that there's two of them. But then we're going to look at y equals 0, which says that uv is equal to 0, and that is equally bothersome. Right? Okay. And then for the x plus y equals A, once we do the work for x plus y equals A, then the equals B will be obvious, all right? But when we substitute in there, x is u minus uv, and y is uv. So since we're saying that, then, come on, u equals A. And then, of course, x plus y equals B will transform into u equals B, okay? So what that tells us is that up here in the u equals 0 appearing there, we don't really want to use those because that would end up being parallel to these. And so it'll throw off kind of what we're doing with stuff. All right, so I'm going to add a page here. And on this page, I'm going to draw, come on, there we go. The UV plane, UV. And I'm going to come back over here and I'm going to copy these things here and just paste them over here, and then we'll move them around where we can look at them nicely. So I'm going to have to draw u equals A, u equals B, v equals 0, and v equals 1. So I don't know what A and B are, but they need to be positive because if they were not positive, then our picture that we had over here would not have ended up in the first quadrant, and it's got to be in the first quadrant. Okay, so negative values for A and B would end up being, it would have ended up giving us a region that didn't make sense. So I'm going to go ahead and draw here. Maybe it'd be a good idea drawing wise if I change the color on my lines to being green and make them here. Sorry, here's the point at which being a little bit obsessive might be a bad thing. All right, so one of those will be u equals A, and one of those will be u equals B, all right? And then the V equals 0 there, and V equals 1 here. And I don't really have any sort of notion about the distance between these and stuff, but I'll kind of try to shade in my region there as best I can. Okay. All right, so that gets me in my region. And now I've got to actually look back to the previous page because I don't remember what the integral is that I have to set up. So the integral is the integral of xy dx dy. Okay. So I'm going to write down here integral across, it called it d, of x, y, dA. And for clarification's sakes, maybe I'll put that as dx, dy, or dy, dx or something. And then I've got to do another integral here. And I've got to think about what x, y would be. X we said was u minus uv, and y was uv. And now we're going to say du dv. Doesn't matter what order because it's rectangular. Okay. So the outside one goes 0 to 1, and the inside one goes A to B. We do have to keep track of, you know, which is which on that sort of thing. But in any case, though, so far as evaluating it goes, we have one of those nice conditions again. I will recopy it, but I'm going to factor out the u there and have a u squared. And then I have v minus v squared. I can say du dv. And we've had this sort of nice thing happen before. 0 to 1 v minus v squared dv, integral a to b of u squared du. So with the dv one, you end up with 1/2 v squared minus 1/3 v cubed. V is going from 0 to 1. And I'll put some brackets around that. And then multiply by, on the other one, just 1/3 u cubed, going from u equals a to u equals b. So plugging in on the first one, you have 1/2 minus 1/3 is 1/6, minus 0 is still 1/6. And then on this other one, you have 1/3 b cubed minus 1/3 a cubed. So we'll have 1/18, and it's b cubed minus a cubed. Yay, then we're all done. Okay. So I hope that worked out. And then we're going to charge right on to another one. All right, so the next one asks us to find a linear transformation that maps the UV region 0, 1, 0, 1 to the XY parallelogram P with the vertices. Oh my God. And I'm realizing something. We did this one in class already. Okay. So I'm going to leave this one off and go on to the next one. All right. If I were better at editing videos, I would just cut this portion out. I'm not. So, all right. So the next one asks us to use a transformation to do the double integral cosine y minus x over y plus x dA, where R is a trapezoid with those vertices. Okay. We're going to sketch both regions. So we'll start with the one that's in the XY plane, because that's always kind of more in our wheelhouse. And everything was in the first quadrant, so keep that in mind. And it looks like we're only going 1, 2 units, 1, 2 units. This is actually looking a lot like that earlier one did, right? Because if we're going to do a trapezoid connecting those, then surely it's got to be that and that. And so the thing we've got to do is to pick out our transformation. Now, if you write the equations of those lines, this one is x plus y equals 2, and this one is x plus y equals 1. That suggests a good choice would be u equals x plus y. And then if you want to get your v to work out there, if we look into what we're integrating, then it seems like another good choice would be either minus x plus y or x minus y. Either way totally ought to work just fine for this. Okay. And I did forget to do the standard thing of trying to shade this in so that it looks, a little bit better. Okay. So if we're doing that there, the problem is, oh no, I started to say a problem, but the problem is because I was confusing it with exercise 3, or exercise 4. Right? But in any case, we do have the difficulty, since we chose u and v rather than having x and y given to us, we have the difficulty that now we have to solve for x and y. If you choose linear transformations, you can always find a way to add and subtract multiples of u and v to try to eliminate one of the variables. So in this case here, if you'll notice, u plus v would be 2y. So that says that y is going to be u plus v over 2. And I can't write very well right now. Then on the other hand, if we were to say u minus v, notice that that would get us a 2x. So, all right. And then when we want to do our partial of the transformation, or the Jacobian matrix there, we are doing a determinant, and we will get 1/2 when we take it with respect to u, and minus 1/2 when we take it with respect to v. The it there was the x, sorry. And the bottom is the y's, and we'll get a 1/2 on both of those. So when you multiply those, you will get 1/2 times 1/2 minus 1/2 times negative 1/2. So 1/4 plus 1/4, which is 1/2. Okay. All right. So once we've got that, then we're going to need to actually do the transformation and stuff and see what happens. All right. With doing the transformation, you'll have to go ahead and label here. I start to write u, not at the u yet, dude. Y equals 0 and x equals 0 for those lines on the side. Okay. So if we go ahead and look at the nice stuff, x plus y equals 1, then we can see that that is going to be u equals 1 and x plus y equals 2. Well, that's going to be u equals 2. And then the x equals 0, well, that's going to be x plus, oops, I lost my place. That's going to be u minus v over 2 equals 0, but that's just u equals v, right? And then y equals 0 is going to be u plus v over 2 equals 0. And when you solve for it, then you can say v equals minus u, or put the minus whichever way you want to put it there. Okay. So I'm going to go ahead and copy those off there like I did last time. And I'm going to add a page. And I'm going to paste. So, and put those together there. And let's see. If I'm doing the orientation where the U is horizontal and stuff, then it'll look like that. And so U equals 1 maybe would be here. And U equals 2 then would be here. And then V equals, okay, now I may have gotten in trouble with my drawing. U equals V is going to be this line here that's going up with a slope of 1, but then U equals minus V needs to be going down here with a slope of -1. Okay, so clearly I didn't quite think that out. And I am going to need to draw more for those lines. And great. As I did it, it decided not to help me out. And okay, I think that's good enough. And maybe I'll put that up there. And so because interior should go to interior on such things, then I would expect, come on. Yay. Okay, that didn't look too bad. Since interior should go to interior, then I would expect to go ahead and shade in stuff roughly like this. And I shrunk my page when I should not have. I should have made this bigger. Okay. All right, and it's got a smudge in the middle of it, and I'm not going to worry too much about my artwork. Okay, I will worry lots about my artwork, but I would hope that you all aren't bothered too much by it. So, all right, we are now going to set this up, and I have forgotten what the integral was. Oh, it's that weird one there. Okay, so double integral across, did they call it R or something? Yeah, R cosine of y minus x over y plus x dA. Okay, and then as before, I'm going to go ahead and label that as dx dy so that we kind of clarify, you know, what coordinates we're talking about and stuff. And so this new region, since the old one was R, maybe the new one will be S. So we'll have a double integral and stuff. We don't really need a name for it. And we'll have the cosine of, now y minus x, if you look over there, is going to be just v over u. And then we need to say the Jacobian, which turned out this time to just be 1, and then d something, d something. The easiest setup here is going to be dv, then du. Okay. So with regard to that, then we will say that the u's are going from 1 to 2. And when we are between 1 and 2 for our u values, that you can draw an arrow. I started to just draw it temporarily, but I'll leave it where it marks it and stuff. An arrow going up in the direction that V increases, and we'll have to get that it hits negative U and then exits at positive U. Okay. So we are going ahead and doing that integration here. And if we're integrating that with respect to V, then you can think about the 1 over U that is inside there as just being a constant. And that means that when you integrate it, you will end up with an extra U cosine of V over U. And the V going from minus U to U. And then we'll have a du afterwards after we evaluate it all. So we'll integrate 1 to 2 still. When you plug in the U, you will have U cosine of 1, geez, minus U cosine of minus 1. All right. Now, here's something that you may or may not spot. Cosine is an even function. That means that the cosine of minus 1 is the same as the cosine of 1. So that means that we have here 0. And the integral of that's really easy. Okay, so that's what was going on with that. Hopefully that makes some sense. And then we will race right along and tackle this number 6. Now, looking at the number 6 here, and we've got this x plus y and this e to the x squared minus y squared. Looks like a terrible mess, but the x plus y, or the x minus y and x plus y keep appearing over and over again. So that suggests the transformation, and it's a transformation we've already used. So we're totally going to take advantage of that. All right. So I'd like you to go ahead and try this one without my help. Okay. And then just pause the video, give it a shot, and see what's going on, and then come back, right? All right. So I'm assuming that you're back and that you've already tried this. So when you did that, you hopefully tackled it the same way as we tackled these other ones. And so you drew a picture of the XY region first. So, and then I have a phone call. So I will stop sharing because I got to do that, and I will pause. Hey, I'm back. That was Colton from Rocket Mortgage. So I didn't call Rocket Mortgage. All right, so, oh, I guess I have to reshare screen. One of the annoying things about Zoom is that you cannot pause in the middle of sharing screen. So, or if you can, it's just a trick I have not learned yet. All right, probably for the best, because I might just walk away from the computer and not remember I was sharing screen for like an hour or something. All right, so we're going to draw our XY plane real quick here. And you know that lines like these are going to be lines with a slope of -1, because we've seen some examples like that already, which suggests to me that I might need to kind of move these axes around a little bit. So, all right. So I'm going to draw lines that I think look like they've got a slope of -1, like so. And I'm just going to grab that and try to position it in here, because x plus y equals 0 ought to go through the origin. And then if I have, you know what? That doesn't look very much like a slope of -1 to me, but okay. but as long as I have the two lines being parallel, it should be good enough. Okay, so hopefully that'll be good. I'll try not to worry too much about it. All right, and then lines like these that have x minus y equals 0 or something, those are going to have a slope of 1. So I'm going to try to just make myself a couple of lines that look kind of like they have a slope of 1 and call it good enough. Okay, I think those are parallel. So x minus y equals 0, so we'll have to go through like that. And x minus y equals 2 should end up having, and sorry, I'm going to have to actually figure this out. That would end up being y equals x minus 2. So it should end up having a negative intercept. So, and x plus y equals 3. All right. So I think these are going to look kind of like that. And I will tidy this up just a little bit here in a minute. So this place down here is minus 2. This place over here is 3. But this place here would need to be 2. Okay. Yucko. All right, I spent way too much effort drawing my picture there. Sorry about that. But then I'm going to move it up here. And I'm just going to go ahead and put labels in here. You may not really need them, but x minus y equals 0, x minus y equals 2, x plus y equals 0, x plus y equals 3. And then I feel like I ought to try to shade it in. Don't waste a lot of effort with shading though. Okay. All right. And so now, because of the fact that we kept running into x plus y and x minus y everywhere, the obvious transformation is to do this. And like we saw last time, we can then solve for the x by adding those two things and doing that. And then for the y, you can get that by solving like so. And our partial of xy with respect to uv, the Jacobian, we're going to come through there and have 1/2, 1/2, and 1/2 minus 1/2. Okay. And so when you do that, you will end up with minus 1/4 minus another 1/4. So you end up with a minus 1/2 out of this. Okay. Now, advice in your textbook is going to be to throw away the minus sign. I would advise against that. It depends on what kind of application you've got. If it's something where you can tell whether getting a positive or negative number whether it makes sense that you would be getting a positive number or that you would be getting a negative number, then do that. But if you know that you have to use a certain transformation for something and the number you get back could be positive or it could be negative, I think you're playing it safe to go ahead and do it like this. But the problem is that by swapping u and v here, and I was choosing the u and the v, right? By swapping just their names, I could have gotten a positive 1/2 out of this instead of a negative 1/2. So I'm not giving you super good answers on this. I can tell you though that when I grade things, I will give you the benefit of the doubt on that little thing about a change of variables. Okay. So, all right, but I'm going to go ahead and work through the problem with the negative 1/2 in there. Okay. I am going to stop and talk a little bit though. So the reason why this is a thing is that there's this this thing that we do in linear algebra about changing variables and doing this thing called change of basis. And when you change bases and the new basis flips things around, it doesn't mean much to a drawing to flip things around. But if your application is something where you're applying linear algebra to transformations that are actually stresses and strains on an object, say pylons that are holding up a bridge, and you get a negative Jacobian coming out of it, what that means is that it is going to turn the pylon inside out and break it. So throwing out the negative sign is a really big deal in certain applications. They are not the applications we're working on. So it's okay that the calculus book does that, but I need you, if you're going into engineering and building bridges I might drive over, I need you to know that this thing that calculus books do is wrong. So, all right. Returning to the non-inverted bridge. Sorry, this has been something that has worried me a lot since I've taught this material a lot. So, all right. So now we're going to get our picture of this new region that we've got. And yeah, I forgot to change colors there. Boom. Boom. And I probably drew too much of it. All right. So keeping in mind, yeah, where am I? Where am I? Okay. X minus y equals 0. That is v equals 0. So really we've got v equals 0 and v equals 2. Okay. So if this is u and this is v, then I need to draw a horizontal line here of v equals 2, and then label v equals 0, the u-axis. And then the other two is going to be u equals 0 and u equals 3. So likewise, I'm going to draw a vertical line, label it u equals 3, and then u equals 0 for the v-axis. And then our shading stuff, just do the best you can. A quick job with that. Okay, good enough. All right, well, the great thing out of that is that now our double integral across r of x plus y e to the x squared minus y squared dx dy, well, that's going to be equal to an integral x plus y. What was that? That was u. And e to the, now x, if you just go ahead and multiply those out, you'll get some nice things happening. But if you spot that x squared minus y squared can be factored as x plus y times x minus y, then you can go directly to calling that uv, okay? And looking at that, I think I want to go dv and then du, okay? The reason I want to go dv and then du is that if I do it du dv, I have to do integration by parts. If I do it dv du, then I just have to do a u substitution, okay? But in any case, the u values, where do those go between? 0 and 3. And the v values go between 0 and 2. Nice rectangles and stuff, right? Although I am going to end up going onto a second page, I'm not going to end up doing very much on that second page. So I'm just going to grab this integral here, make a new page, paste my integral, put it up there, and say then this is equal to integral 0 to 3. And if I, doing the other integral, if I say w equals uv with the notion in mind that v is a variable and u is a constant, then dw is going to be equal to u dv. And we can see that we have a u dv to put together there. And so we would be dealing with an integral, yuck, this is extra work, sorry. An integral of e to the w dw. And then we have a du to deal with. And I always advocate going ahead and plugging things in so that here you would say when v is equal to 0, w is also equal to 0. When v is equal to 2, w is 2u, which is, you get the pun? 2u is double u. Okay, that was terrible, terrible, terrible. But it is super easy to work this out at this point because we'll say e to the w going 0 to 2u, and then a du afterward. I should put some brackets in there. And so then this is equal to integral 0 to 3 e to the 2u minus 1 du, and that's going to be 1/2 e to the 2u minus u goes 0 to 3. So 1/2 e to the 6th minus 3 minus 1/2 e to the 0 minus 0. So we end up with 1/2 e to the 6th minus 7/2. If you want to factor the 1/2 or something, great. Okay. I could never see any reason why you would need to approximate this, but if you need to approximate it, you approximate it. In general, though, unless you have a specific application in mind and you know what you're going to do with it and stuff, I would say go ahead and do the integration just to make sure you can do it. Okay. I know that the calculator can always do this for you, but you know. All right, so here's another one. And this one asks us to use a transformation to evaluate e to the x plus y dA, and the r is given by absolute value x plus absolute value y is less than or equal to 1. So let me sketch this region, and we'll see why we end up using the same transformation over again. Okay. But yeah, give me just a second on this because of the fact that I'm trying to draw a square and I'm not super duper confident my square will end up being square. Okay, it just isn't, so I'm going to do something different. Okay, because I'm going to copy, paste, 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 and rotate. Okay, that was a bad idea. Okay, that was a bad idea because whenever I rotate these, it resizes them automatically to whatever the damn size it feels like. Okay. So the reason that, oh, come on now. Oh, I will pause now. Okay, friends, unpausing. Sorry about that. I was being very frustrated about my ability to draw. Given unlimited time, I'm a really good artist, but there's no need for you to watch the 5-minute video of me drawing straight lines. So when we say absolute value of x plus absolute value of y is less than or equal to 1, of course, to get the edges, you want to draw x, absolute value of x plus absolute value of y is equal to 1. So what that means is that your x or your y, either one could be negative or both could be negative. If one of them is negative, then its absolute value is actually the negative of the number, right? So when we talk about absolute value of x plus absolute value of y equal to 1, we actually have to think about all the possible plus and minus combinations here. And mapping these out real quick here, we get the x minus y equals 1 or y minus x equals 1 possibilities. And those are giving us things in the second and fourth quadrant. And of course, x plus y, minus x plus minus y equal positive 1 is going to be the same as having x plus y equal to 1. So our region that we're thinking about is this diamond shape. It is actually a square, but at a 45-degree angle. Okay. But once you see those, you see why that same transformation has been coming up over and over again is coming up. I'm going to look back at what we did on it last time, and I am going to purposely swap the u and the v this time. Okay. And yeah. So that may cause some difficulties there with kind of the intuition of what you're doing with it. But I want to suggest to you that if you do it both ways, you should get the same answer, but that you have some changes about how things get set up as you go along. Okay. So last time I ended up with the u equals the x plus y, and this time I'm going to put u equals x minus y, and v equals x plus y, so that when you solve, you get your x is u plus v over 2, and your y is, which one? Hang on. Let me look back and see which thing I had. V is x minus y, so okay. I hope this doesn't come back and bite me again. Okay, to get the y, you say v minus u, so you have minus u plus v over 2, and that, yeah, that is what I want. Okay, so our partial of xy with respect to uv then is going to be equal to the 1/2 up top is no problem, but the minus 1/2 plus 1/2 here means that you have the 1/4 minus a negative 1/4. So we end up with a positive 1/2. Okay. By the way, dropping the negative on this problem would cause you to get a 0 out of the Jacobian. And with the interpretation that the Jacobian tells you how much a region is stretched, then that would suggest that you are taking a region that has area and turning it into a region that has 0 area. And that would be a problem. So if you drop a minus here and get a 0 Jacobian, you need to recognize that that's what happened and go back and find the error. Okay. All right, so now we're going to need to do something with the UV plane. And this should be relatively easy to do if my artwork doesn't end up giving me problems. So I'm going to copy that, paste it. I'm going to copy that and paste it. I'm going to put the two of them together and change the color to green because I kind of like that. And then I'm going to copy and paste again because I need to have some horizontal lines and some vertical lines for this. All right, so we'll go back here, label this as U and this is V, and we can hopefully see that we're going to have a U equals -1, a U equals +1, a V equals -1, and a V equals +1 from doing those transformations. Notice that I didn't go through all of the painful steps of substituting this time. What I did was to just make the observation that we had the x plus y and the x minus y being set equal to plus and minus 1, and those were our U and V. So I'm just saying that you should kind of get used to that sort of trick on it. And then we're going to have our integration, and it's going to be super nice to set up. And we will have an e to the, let's see, x plus y is the v, okay? And we can say du dv or dv du, does not matter because we go -1 to 1, -1 to 1 on both of them. Now I'm going to try to get away with doing my integration on the same page here. So I'm going to kind of condense that a little bit and remind us that we get to do -1 to 1 du with nothing in it, -1 to 1 e to the v dv. And so the integral with the du is just going to turn into 2 because you get u, evaluate 1 and -1 and subtract. And then the e to the v, we're going to plug in a 1 and a -1. And I think that's fine, a fine way to leave it. If you want to write 1 over e for stuff, go ahead. Okay. And if you need an approximation for something, approximate it. Okay. All right, cool. All right, then let's see. Oh, is that the last one? That is the last one. Yay. So not that I don't enjoy being here at 9 p.m. making a video when I should have done it yesterday, but yeah, hopefully that is helpful to y'all. I'll see you